The next topic we're going to look at is something called electromagnetic induction. And this was discovered back in 1831 by Michael Faraday. Again, you don't need to memorize names and dates for these. But he discovered that a conductor that moves through a magnetic field will produce an electrical current, and that's what we refer to then as electromagnetic induction. And that really is the basis then for all electrical generators. You produce movement in a magnetic field, and then that's how your electrical current comes out. And all of your hydroelectric dams, your coal-fired power plants, all of those are actually operating then on this principle. So we are going to be looking at a slightly simplified view of this one here. And so what we're going to do is we're just going to take a conducting rod and we're going to be moving it then through a magnetic field. And as we do that, we want to be moving perpendicularly to the field. And so our maximum there is going to be when it's perpendicular. And this will be a sine theta relationship again. And so when it's 90 degrees, your sine theta goes to 1. If we're running parallel, we're not going to get any current running through here. So if you're moving parallel to the field, there will be no induced current. And again, that's just because the sine of 0 or sine of 180 is going to give us then 0. Now, we're not actually going to look at the equations for these, but that's how those ones are going to go. So you need to know just those two cases, perpendicular to the field, and that's how they'll generally be set up. But if it is running parallel, then just make sure you know there is no induced current. Now, this particular one has the bar moving in this direction, and so our current is moving downwards. We'll get to the rule for that in just a moment. But if I reverse that velocity vector, then I'll also then reverse the direction or the electron flow in there as well. And so the direction that you're moving that through there is going to determine then the direction then of the current going through the bar. Now, if you just have a bar not connected to anything moving through there, you will just get basically a concentration of negative charge on one side, and so that'll leave a positive end on the other. But if we connect this to an external circuit, so we have here, then we have then a whole circuit then attached. This will be a resistor. You put a light bulb or something in there. The current will then just go around there, and in that case, it will act as a battery. So watch your clockwise and counterclockwise with this. So right now, the electrons are flowing down through here. So they're just going to follow their wire basically through to complete the circuit. And so in that direction there, that's going to be going counterclockwise. If I change my velocity vector to the other direction, my electrons will be going up and then around in this direction here. And so that'll be the clockwise direction. And so when these are attached to circuits, you very often will see clockwise or counterclockwise given then as the direction. So make sure you're keeping those ones straight. Now, conservation of energy is still going to be applied here. So we are producing electrical energy. And so that electrical energy that's produced must be equal then to the work done in moving the rod through the field. Now, we are taking into account here just the frictionless case overall. And so that does kind of depend on that. Now, if there is friction involved, then we'll have actually a little bit more work done moving the rod than we're going to get back out in electrical energy. Now, the direction of that induced current is given by something called Lenz's law. And the induced current is just the current that is produced by that moving bar there. And what Lenz's law says is that the induced current is going to flow in a direction as to produce a magnetic force that opposes the direction then of that applied force. And so if we draw in our forces for this one here, I have a velocity vector that's moving in this direction. And so to create that motion in that direction, I need to put in then an applied force. And so that applied force will always be in the direction of that velocity vector. And that's going to be moving it then in that particular direction. And again, if we change our velocity vector, we'll change our force applied. In this diagram, it's going towards the right side of the page. And so what Lenz's law is telling us then, that I produce an electrical current here that results in a magnetic force that's going to be opposite then to that force applied. And so that's the key then just to that Lenz's law, is wherever you see that velocity vector, and that's more common than the force applied, but either of those are always in the same direction, your magnetic force is always going to be opposite to that. And so that's how we'll come up with the direction then of our electric flow. Now, the hand rule we're going to use is just the same one we used for any wire in a magnetic field. You're going to take your left hand. You're going to place it flat so that your fingers, your palm, and your thumb are all kind of at 90 degrees from each other. You're going to take your fingers in the direction of the magnetic field. So in this case here, my magnetic field is into the page, so down straight into the page. My thumb is going to be in the direction of that electron flow, so that's down also towards the bottom of the page. And then what you notice is that your palm is going to be oriented then towards the left side of the page, which is that force magnetic. So we have used this left-hand rule before. Again, for conventional current, use your right hand. But make sure that you are using always the magnetic force and not the force applied. And remember that magnetic force is always opposite the direction of that velocity vector. Now, this idea of that opposing magnetic force is required for conservation of energy, and so that's the key really to Lenz's law, or why Lenz's law really exists, and why those forces have to be in opposite direction. So remember that we're dealing with a frictionless case here, and so if this bar here is moving with some velocity or constant velocity, now it will take some force to get it moving, but once it's moving at a constant velocity, if there is no friction, I shouldn't need any applied force to keep it moving. And so if I'm not adding this applied force and I'm still getting electrical energy, that would mean that the conservation of energy is being violated because I'm producing energy without having an external force. However, because I'm getting this opposing force over here, I have to keep pushing this one here in this direction in order to keep that bar moving. And so if I get this bar moving and I stop applying a force, this magnetic force is going to bring it to a stop fairly quickly. So I always have to keep applying this force in order to produce that electrical energy, because this magnetic force that shows up opposes the motion and ensures that I always have to do work to keep that bar moving through then that magnetic field. So let's look at a couple of direction problems here. Now remember, we're going to be kind of doing two main things. Number one is the force applied and velocity vector. Those are in the same direction, but they're always opposite to the force magnetic. And then once we know the direction of that force magnetic, then we can use that hand rule. Palm is the force magnetic, your thumb is the current, and your fingers are the field lines. And then we can solve for our directions from there. So in this case here, we're looking for the direction that this one must be moved. And so the direction that it must be moved, that's going to be my velocity vector. But remember, that's also always that force applied vector. So that's what we're going to be looking for in this case. So we're going to take our left hand, because we'll be dealing with electron current. My thumb is going to be pointing to the bottom of the page. That's my current direction. The fingers are going to be pointing to the right side of the page. And over here, that's my magnetic field direction. And so we see that our palm is pointing straight down. So straight down into the page. Now remember which force this is. This is my force magnetic, not the force applied. So the hand rule gives you your magnetic force. Now what we're interested in is this velocity. And remember, then your velocity is just opposite the force magnetic. So if my force magnetic is down into the page, then my velocity vector, now this could also be written in as a force applied, but if we're looking for direction, we typically look at it as a velocity vector, is going to be coming then directly straight out of the page. The next one, we're going to be looking at our induced current direction, and so that'll be through this wire, either up or down. Now my velocity vector is going in this direction, which means that my force applied is in this direction as well. Opposing that is going to be my force magnetic. And so once I know my force magnetic, now I can do my hand rules again. So my palm is going to be pointing towards then the left side of the page. That's this force magnetic. And my fingers are going to be pointing directly up and out of the page. That's those magnetic field lines. And what you'll see then is that your thumb is pointing towards the top of the page. And so my current running through the wire then will be moving towards the top of the page. So here we're looking for the direction of that applied force, which would be the same as the velocity direction. So we'll start here by finding the magnetic force direction, and that will just, of course, be opposite to that. So the thumb of my left hand is pointing to the right side of the page, and my fingers, because these are X's, are going to be pointing down and into the page. So that means that your palm is going to be pointing towards the bottom of the page, and that will then be the direction of that force magnetic. Don't forget, though, that the force applied is always opposite the force magnetic. And so the force applied, which is what I'm looking for in this question, is going to be pointing up and to the top of the page. For the last one, we're looking for the magnetic field direction, given the velocity vector and the current. So again, this is my velocity vector. So this is also my force applied. And so the relevant force for my hand rule is going to be this force magnetic, which is now pointing to the left side of the page. So our thumb is going to be pointing to the bottom of the page. That's my current direction. My palm is going to be pointing towards the left side of the page. That's this force magnetic. And we see that my fingers then are pointing down directly into the page. And so my magnetic field will be then those X's going into the page. Now, the last case we're going to be looking at here is a solenoid. Now, this will still follow Lenz's law for the electromagnetic induction. But what we're going to be doing here is just doing that with a solenoid. And so if I take a solenoid and I move it relative to a magnet, and so I can move the magnet into and out of the solenoid, or I can move the solenoid relative to the magnet, or I can move both. In either case, I'm going to induce a current then in that solenoid. And that direction of the current will again be given by Lenz's law, which tells me I need to have an opposing force. So if the solenoid and the magnet are moving towards each other, that current is induced such that I have a repelling force between those. Again, because it's always trying to oppose the motion. So if I'm trying to push these ones closer together, the magnetic force that's produced has to be trying to push them apart. Now, when you're kind of thinking through your directions, remember that the solenoid can act like a bar magnet. And if I have two magnets and I want a repelling force between them, what I need to have is I need to have like poles. Now, in this case here, I have the north pole moving into the solenoid. That means that I'm going to get a north pole generated on this end of the solenoid. If I flip the bar magnet, then I'll flip the current direction. And so if I'm trying to push them together, what I need to have happen is I need to have like poles kind of where those two are coming together. And those like poles, in this case they're north poles, but they could be south poles as well, those like poles then are going to give me then the repelling force that I'm looking for. Now for your current direction, if I want a north pole here, so going back to the rule for solenoids, we're going to curl our fingers in the direction of that current. So here if we look at our current flow, the current is moving up the front of the magnet and then down the back of the magnet. And so if you curl your fingers of your left hand in that direction, your thumb is going to be pointing to the right side of the page, and your thumb, remember, points to the north pole of that solenoid. And so in that case then, I get my two like poles, and that's going to give me then my opposing force. If we go to the case where we're moving those two apart, so again, either the solenoid or the magnet is moving, but they're moving away from each other, the current is going to be induced such that I get an attractive force between those. Again, if I'm trying to move them further apart, the opposing force is going to try to pull those back together. And pulling things back together, remember, I'm going to need then opposite poles because opposite poles are going to attract, and so if I want that attractive force there, I need opposite poles. And so if I'm taking this north end of the magnet and moving it out of the solenoid, what I'm going to do is I'm going to induce then a south pole over here. So to do that, my fingers are curling, in this case here, up the back side of the magnet and down the front side of the magnet. So up along the back, down along the front. That puts your thumb basically to this side, to the left side of that solenoid. So that means that's your north pole. So this is your south pole. And so then I have those opposite poles, and then I will be getting that attractive force. Now, a couple things to keep in mind. If I change the direction that the magnet's moving, I change the direction of current through here. So if I take this bar magnet and I push it into the solenoid, I get my current flowing in this direction. When I pull it back out of the solenoid, my current direction then is going to reverse. So watch carefully for that. Now the direction that the wires are wrapped around the solenoid is also going to matter for the direction there, so be careful of that. And then also whether I have a north or a south pole kind of in the solenoid for there. So there's really three things that can change that current direction: the way the wire is wrapped, whether you're moving the magnet into the solenoid or out of the solenoid, and then whether the poles of the bar magnet that you're pushing in or out of that solenoid.